Hey everyone, I'm Shah. In this video, I'm going to talk about the recent wave of reasoning models, which have been trained through reinforcement learning. While there has been a lot of hype recently around DeepSeek R1, my goal with this video is to give you a sense of how models like O1 and R1 work under the hood, and through that, discuss why this is a promising direction for AI development without any kind of hype. This will be a somewhat technical talk, but I have attempted to make this very accessible, so you don't need a PhD to understand what's going on here. So the whole story with these reasoning models started about 6 months ago when in September 2024, OpenAI put out this O1 model, which had this advanced reasoning capability, which it learned through large-scale reinforcement learning. From a practical perspective, what this means is if you have interacted with O1, you've probably seen this, you'll type in your prompt, like what is the airspeed velocity of an unladen swallow, and instead of just immediately generating text, the model will start thinking. Through the ChatGPT UI, we'll see something like reasoned for 6 seconds, and then after that, we'll have the actual response from the model. Unlike the typical response we see from ChatGPT, which just immediately starts streaming tokens, these responses from this O1 model have two parts. They have this thinking part, and then they have the final response. So seeing this, you might wonder, what's the point of this thinking process other than just taking longer to generate a response? That turns out to be the main insight from the O1 model, which is this so-called test time compute scaling, which is just a fancy way of saying that when trying to solve reasoning tasks like math problems, logic problems, coding problems, things like that, they saw this pattern in the model's responses where basically the more tokens it generated, the better responses it had. This is summarized graphically through this plot, which I re-illustrated from OpenAI's blog post on it. On the left here, we see this so-called train time compute. And so this is summarizing the well-known pattern that if we take language models and we just make them bigger, give them more data, and train them for longer, they have better and better performance. So that's why GPT-2 was 1 billion parameters, but then GPT-3 was 100 billion parameters, and GPT-4 may be like 500 billion parameters or even a trillion parameters. We don't know exactly, but what we do know is that the bigger you make these models, the more data they're trained on, the longer they're trained for, the better their performance. So that's what this left plot is showing. AIME is just a data set of math problems. So the model gets better and better at math the longer it's trained. On the right, we have this so-called test time compute, which basically means the number of tokens the model generated. So we see the more tokens that the model generates, the better its performance becomes on these math problems. So this is the key insight from O1, which is basically training bigger and bigger models is not the only path to better performance. We have this other path on the right, which is generating more tokens. Although this is something that people have known through prompt engineering, so if you've been playing around with LLMs yourself and you've been trying to get them to do what you want, and you find that sometimes it takes you a very long prompt in order to do that. Another version of this is with so-called chain of thought, where you basically prompt the model to think step by step and then to work through each step of the problem one at a time. Both of these things have been observed empirically to lead to better performance, so this is just yet another piece of evidence to support that idea. So in contrast to before, where maybe we pack all this into the prompt or we just prompt the model in a clever way to get it to generate a lot of tokens, O1 works a little differently. So it has these so-called thinking tokens. There are special tokens that OpenAI introduced in the post-training phase, meaning they introduced them after they created the base model. And basically this delimits O1's chain of thought. So it'll be something like this. I don't know exactly what the special tokens look like, but you can imagine it's just something like this, where you have a start thinking token and an end thinking token. And then between these two tags, O1 is going to think through the problem. This is what we saw in the first slide, where the model was thinking through the problem and then it was printing out a summary of its thought process. So it first recognized that it was a cheeky question referencing Monty Python, and then it was actually thinking through the physics of how fast swallows can fly. So this is important for two reasons. one, from a user interface perspective, once you have these clear tags of when the thinking starts and stops, you can know when to suppress the stream to the user. Once your UI sees this starting token, you know not to print it to the user interface. But once you see the end think tag, you can know to start streaming tokens to the user interface. But another cool thing about these thinking tokens is that you have an interpretable readout of how the model is thinking through the problem. So this might be very much like the internal dialogue a person has when thinking through a problem. And it's great because it's in English, so we can read it and try to understand how the model arrived at its solution. Through this, we've realized that doing this chain of thought, letting the model think before answering, leads to better and better performance on these reasoning tasks. But the central question is, how did OpenAI implement this? Unfortunately, they didn't publish the technical details of how they pulled this off. They did share that they used large-scale reinforcement learning to do this, but they didn't really go into much detail beyond that. So for much of the past 6 months, many people have been using O1, but no one really knew how OpenAI did this until DeepSeek, which is a research lab out of China, published this paper which revealed the mysteries behind O1. So the paper was called DeepSeek R1, Incentivizing Reasoning Capability in LLMs via Reinforcement Learning. In this paper, they shared the technical details behind how they developed 2 models. One model was called DeepSeek R10, which was trained strictly on large-scale reinforcement learning, just like what OpenAI said they used for O1. And then in the second model, they used a combination of supervised fine-tuning and reinforcement learning. Of these 2 models, DeepSeek R1 has definitely gotten more public attention, mainly because it has better performance than DeepSeek R10. But this first model is very important and helpful for 2 reasons. One, it generated training data to create R1. But the second, which I find more interesting, is that it gives us a lot of insight on the power of reinforcement learning. And to give the punchline, the amazing thing about DeepSeek R10 is that it learns all by itself through reinforcement learning to do this chain of thought reasoning and to do things like verifying and reflecting on its past responses and thinking through problems. I'll talk through the details of each of these models one at a time. So we'll start with DeepSeek R10. Again, the key feature of this model is that it was trained using only reinforcement learning. Just to compare this to supervised learning, which is significantly more popular, this is where the model learns by example. So to use an analogy, supervised learning is kind of like if I was looking for a new job and so I wrote up my resume, but I wasn't sure if my resume is any good. So instead of applying to a job, I would give it to a recruiter who would read through it and then give me specific feedback and would send me an example resume, which I could compare to my original resume and make some changes and updates to make it more like the one the recruiter provided. On the other hand, reinforcement learning works differently. So instead of teaching models by example, in reinforcement learning, models learn on their own through trial and error. This is very similar to how we might actually learn in the real world, where I might not send my resume to a recruiter or a resume expert, but instead I'll just take my resume and apply to a job with it. And then from there, it's very unlikely that the company is going to give me very specific feedback on my resume or give me example resumes of past candidates who got hired. What's more likely going to happen is they'll just send me an automated message that says you've not been chosen at this time. So this is fundamentally different than supervised learning because now I have to figure out what I did wrong in my resume and then figure out the improvements that I can make to it. So we can essentially follow the same process to train a large language model. So in supervised learning, we can have the model generate an output, and then we can compare that generation to a human annotated, a human labeled output and train the model on this data. On the other hand, with reinforcement learning, we don't generate examples that the model can learn from. Instead, we just take the model's output and then do some kind of evaluation on it. So if this is some kind of like mathematical proof, we can just tell the model it got it right or it got it wrong. Basically, the model has to figure out on its own how to write good mathematical proofs. While there are a lot of technical details behind R10, I just want to highlight 3 key features. The first is the prompt template. So this is basically how example questions are passed into the model. These reasoning models are trained on question-answer pairs, which require require reasoning. In other words, they're trained on things like math problems, coding problems, logic puzzles, and things like that. For training R1 0, DeepSeek used this prompt template. Basically, they're just describing that there's this conversation between a user and an assistant. The user's gonna ask a question and the assistant's gonna solve it, prompting the assistant to think through their reasoning process and then enclose their reasoning process in these special think tokens, and then enclose their answer with these special answer tokens. And then it has a place where the prompt will get injected, and then everything after will be generated by the model. And so this prompt will be a question that requires reasoning with a clear, correct answer. So like math, coding, and logic. The amazing thing here is how simple this prompt template is. It's nothing sophisticated. They're not telling the model explicitly to reflect or verify or do any other kind of reasoning strategies. This was actually something intentional. They didn't want to include any kind of bias in the prompt template and just observe the natural evolution of the chain of thought reasoning the model generates. The second key component here is the reward signal that is passed to the model. This is just like if I apply to a job, the reward signal I get is either they reject my application or they call me in for an interview. So we need to do a similar thing for training R10. Here, DeepSeek had two components to their reward. One was accuracy. All the questions in the training data set had concrete correct answers. Maybe they're math problems like this, where there is a correct value, and you can just use a rule-based checker to see if the answer the model generated was right or wrong. The other component to the reward was formatting. So basically, ensuring that the reasoning process that the model goes through is indeed within the think tokens. Again, this is something that can be rule-based. You can use some kind of logic to ensure all the reasoning occurs within the thinking tokens. The striking thing here is how simple the reward is. And again, this was intentional by the researchers because they suggest these model-based rewards, in other words, rewards generated by a neural network, are prone to reward hacking, which is basically this situation where the model we're trying to train learns how to exploit and trick the reward model to maximize its rewards without actually getting better at the task that we want to train it on. And this is very much how humans operate in any kind of incentive structure. You try to set incentives so people's activities are aligned with the company's goals, but inevitably what happens is that people start to find tricks and hacks and learn how to exploit the incentive structure to maximize their personal gains while forsaking whatever goals the managers had in mind for the company. So that's just to tell you that whether you're trying to come up with incentives for humans or for computers, it's hard either way. So going with very simple ones seem to work well in this case. The final component of this reinforcement learning process is we need to figure out a way to use these rule-based rewards that we're generating to actually update the model parameters. DeepSeek uses this technique called Group Relative Policy Optimization, or GRPO. This is quite technical. If you don't really care about the technical details of how this works, feel free to skip ahead. But for those who are interested, I'm going to explain it step by step. The central question here is how can we incentivize the model to maximize rewards? And so I'll just claim that we can achieve this through the following optimization, which is shown here, where we're trying to maximize this term here with respect to this parameter theta. Let's just unpack what this term actually means. The numerator is the current model's probability of generating an output in response to a question. And so you can imagine in this training process, we ask the model questions, it generates answers, and then we compute the rewards, and using those, we're able to update the parameters. What that means is that at each step of this optimization, the model parameters are being updated and being tweaked. So the model is evolving. Let's say the 10th version of the model's probability is represented by pi theta, while the probability from the 9th version of the model is represented by pi theta old. And so a key detail here is that Q is just some question. So you can imagine some kind of math problem or math question. And then O is some output generated by the old version of the model, by the version of the model using parameters theta old. So we can take that output and compute the probability that the model generates that output using the model parameters. And then we can do the same exact thing by passing in the same question and the same output from the old version of the model, pass it through the new version of the the model and compute the probability that the new version of the model generates this output. Okay, this is all very technical, but what does this mean? What does this ratio actually mean? So the key thing to know here is that this ratio is quantifying how much the current model is deviating from the previous one with respect to this question Q. In other words, it's just telling us how much the model has changed through this single step of the optimization. The other key part of this term is R, which is simply that rule-based reward for the output O. So this is just something we compute using some Python code. No model training, no neural network involved whatsoever. So we have these two components. We have the deviation of the current model from the previous one, and then we have this rule-based reward. But how does maximizing this incentivize the model to maximize the reward? And so just going one level deeper, if this ratio is greater than 1, that means that the output is more probable in the new model compared to the old model. Conversely, if this ratio is less than 1, that means this output is less probable in the new model than in the old one. And then if the ratio is about 1, there's little change in the model. On the other hand, for the rewards, let's say if the reward is greater than 0, that's a good thing, and then if the reward is less than 0, that's a bad thing. Bringing this all together, in order to maximize this whole term, what that comes down to is whenever we have a good reward, so R is positive, we want to make this deviation as big as possible. So we have a positive reward multiplied by a big positive number, as big as we can make it. On the other hand, if we get a bad reward, so we have a negative reward here, then what we want is to make this ratio as small as possible. And keep in mind that these are probabilities, so they exist between 0 and 1. So this ratio is always positive. So basically, we want to make this ratio as close to 0 as possible. Just to summarize, the goal of maximizing this term with respect to theta is to update the probability of generating this output such that the deviations are much greater than 1 for positive rewards, for good rewards, and the deviations are much smaller than 1 for negative rewards. So that's the key intuition. So we can incentivize the model to do what we want, to basically make outputs with high rewards more probable and make outputs with bad rewards less probable by doing this optimization. But it turns out that reinforcement learning can be really unstable. And so there are some measures that need to be put in place to ensure that training is stable over time. So one thing the authors do is implement clipping. This first term is the same exact objective, is the same exact term we saw in the previous slide. But now we have this clipping term. And basically all this is saying is that if the deviations are too far away from 1 to clip it, epsilon is just some parameter we choose. So if epsilon is, let's say, like 0.3 or something, if this ratio is less than 0.7, we're just going to round up to 0.7. And then if this ratio is greater than 1.3, we're just going to round it down to 1.3. That's all the clipping does. It's just to ensure that this ratio doesn't get too small and it doesn't get too close to infinity. Min is just saying that we're going to take whichever of these two values is smaller. So we'll take this original objective or we'll take this clipped version, whichever one is smaller. But still, that's not enough to stabilize training. So they also add this regularization term. Here we have the original objective. Here we have that clipping term. And then we have another term, which is this KL divergence term. Expressing this out mathematically, we compare the probability of the output of the current version of the model to some reference checkpoint of the model that we've deemed good. So they didn't say how they picked this reference checkpoint, but this could be the previous version or every 10th step or something like that. Just some reference version of the model to, again, ensure that training is stable. But wait, there's more. So another part of this is that this is called group relative policy optimization. That kind of comes into play here. So we're not just going to generate one output for a given question, but rather we'll generate a group of outputs, and then we'll aggregate this value over multiple outputs for a given question. That's what this group and group relative policy optimization means. There is yet another component to this, which is that the rewards are standardized at the group level. So we've swapped out the R's with this A term, where A is essentially a standardized version of R, which means we subtract the group mean from each value and divide by the standard deviation. After after all these steps, we arrive at the final objective function that they used for training DeepSeek R1, which is this monstrosity here, but now we know what each component means. This first term is the key thing we want to maximize. This second term is if this probability ratio is too far away from 1, we're going to clip it. And then finally, we have this KL divergence regularization term. When I first saw this equation, I was very scared and confused, but after going through a long process of breaking it down, it now makes sense to me, and hopefully it makes sense to you as well. Okay, so enough of the technical details. Let's see what the performance is. What is the result of all this effort? So there are two things I want to talk about. One is the performance. So this is from the paper, and we can see that the more they train the model, the better and better it gets until it surpasses O1's performance on AIME, which is a standard math problem data set. There are two different evaluation metrics, pass 1 and consensus 16. So pass 1 is how many times the model gets a question right out of like 10 tries or something like that. And then consensus is we're going to generate 16 answers from the model and then do some kind of majority vote to decide what the final answer is going to be. With the second evaluation metric, R10 outperformed O1 with an even larger consensus size, which is remarkable because this was a base model that they just trained through this reinforcement learning process. So all on its own, it learned how to do this chain of thought reasoning and solve math problems. But this is really depicted by this plot here, which is figure 3 from the paper. And you can see the longer the model's trained and the better its performance gets, its average length per response gets larger and larger. So this is another piece of evidence toward this test time compute scaling, which we saw in O1 on an earlier slide. So this is very interesting that we're able to get better and better performing models just by generating more and more tokens. But I would say the most striking thing about R10 is actually reading through its chain of thought reasoning. So it's going to have these long chain of thoughts with this like reflection. So I asked R10 this question: if it takes me an hour and a half to write a code base and my intern 8 hours, how long will it take us both to write 3 code bases? It just starts going off and it starts thinking through the problem. To solve for how long it will take both you and your intern to write 3 code bases together, we first need to find out how many code bases each of you can write per hour individually. And then it has a very long chain of thought, and then it kind of has an answer here. And then to make sure everything makes sense, it rounds it. However, we need to make it more human friendly, so convert it. It's kind of like thinking through and doing all these like weird reasoning things, which it learned all on its own, which is really interesting. But it also learned this verification step. Again, if we recall the prompt used to train this model, there was no guidance. It just said think and then give an answer. Those were the only constraints. But the model learned that it's helpful to do this verification step, and so it has like a long verification process, and so I truncated it because it's quite long. And then at the end of it, the model gets the answer right. So 72 over 19 hours, so it's approximately 3.79 hours. There were a couple key limitations with R10 because it is just learning on its own by trial and error. Kind of how if we learn things by doing and trial and error, sometimes we can learn some pretty quirky routines and habits and behaviors. But one of the things was readability. The model doesn't always format responses properly, so it doesn't box its final answer or it doesn't use markdown, so it's hard to parse the final response. But another big one was language mixing. So if you ask a question to the model in like French or Spanish or German or basically a language that's not English or Chinese, it just replies in English. So an example of this is I asked it add 3 plus 5 in French, and it just gave the whole answer in English. So there's this language mixing, which isn't great for like a downstream use case. To fix these things, they created DeepSeek R1, which is the model that's more popular, it has better performance, and the one people are excited about these days. And so DeepSeek R1 was trained in a more sophisticated way. It did use reinforcement learning, but there were these other steps in the training process. So it starts with DeepSeek v3 base, which DeepSeek published in December of 2024. And the first thing they did is instead of just having it go off and try to learn on its own, they gave it a lot of examples of reasoning data. So they gave it long chain of thoughts to show the model, okay, this is the format you need to use. This is how you can think through problems. This is how you reason. So this is like learning by example, just like the recruiter giving me a bunch of resumes of people who were hired at the company that I want to apply to, so I can make my resume similar to those. Step 2 is doing this R10 style reinforcement learning. So first you do the supervised fine tuning, then do the reinforcement learning like we just saw in the previous slides. And then there's another supervised fine tuning step, but instead of just training on reasoning data, it's a mix of reasoning data and not reasoning data. And then finally, some more reinforcement learning, but also some reinforcement learning with human feedback, which is what was used to create Instruct GPT, which was the model behind the original version of ChatGPT. The output of this is DeepSeek R1, which is a state-of-the-art language model, at least it is today. Okay, so let's go through these steps one by one, and I'll just kind of give sketches of each of these steps, and if you want more details, you can check out the paper. But I will say, as much as the paper reveals about what it takes to create one of these models, they don't go into a whole lot of detail about their data set, and they don't actually share their data set. So that's like an important thing to keep in mind. But I think reference 4 is a open source data set from Hugging Face that they're starting to put together, and that'll give you a good idea of the type of data used to create these reasoning models. This is a question from that Hugging Face data set, and so it has a math problem, and then the data set includes the worked solution. So these both will be passed to DeepSeek v3 base to learn how to reason. The authors describe 3 different sources for this reasoning data. One, it's few-shot prompting. So you take a question, you have a long chain of thought example, I guess human generated like we saw in the previous slide, and then the right answer. And it's all formatted in the way that they want the final model to format answers. Another one is to prompt reasoning. So instead of giving examples of long chain of thought in the prompt, instead they explicitly prompt the model to think step by step, to reflect, verify, the kinds of things that people have been doing to try to get models to generate chain of thought reasoning over the past couple of years. And then finally, they use data from R1.0. So they would take R1.0's template and generate a response from it, and then use that as training data. So after, I think they used thousands of supervised fine-tuning examples for step 1. Then for step 2, they do this R1 style reinforcement learning. So just like what we saw previously, but then they added this language consistency reward to help mitigate that language mixing problem. Again, we have the rule-based accuracy, rule-based formatting rewards, but then they add this language consistency reward, which was basically the percentage of the target language words used in the chain of thought. If we asked the model, "Puedo ir al baño," which is, "Can I use the bathroom?" in Spanish, and then the model generates the chain of thought, it's mostly in English. So this would be like a language consistency score of 4%, because only about 4% of the chain of thought is in the target language of Spanish. So this is just a way to incentivize the model to think in the same language as the prompt. Step 3 is to use mixed data. So the key thing here is it will show the model when and when not to reason. This is actually a pretty funny point. So if you go to R1.0 and you just type in hello or hi there or something like that, it's going to generate an output like this and just start solving math problems. So talk about antisocial mathematician or insert any technical discipline there. This just goes to show you that the model, when you only fine tune it on math and reasoning problems, it doesn't really help you in other situations. To mitigate that, they have some reasoning data, which is one generated by the checkpoint of the model that comes out of step 2. So they get long chain of thoughts from there. And they also incorporate here non-rule based rewards. So basically they use DeepSeek v3 as a judge in order to generate rewards for a subset of the reasoning data. This just allows the model to learn from more flexible prompts which don't have a concrete right answer. So there were 600 samples of this, and then there was also this non-reasoning data, which a lot of it was taken from the supervised fine-tuning data set used to train DeepSeek v3, and they also generated synthetic data from DeepSeek v3. They also hard-coded some responses to questions like hello or who are you, what are you, self-cognition kind of questions. And then there were 200,000 examples of non-reasoning data. The final step is to do more reinforcement learning, but then additionally reinforcement learning with human feedback. So this is basically to just make the model's outputs something safe for humans. So something that humans can actually understand and read and is helpful to us. So again, it's this R0 style reinforcement learning. So with accuracy, formatting, language consistency, but also this reinforcement learning with human feedback, training the model along these 2 dimensions of helpfulness and harmlessness. And since you can't really write rule-based rewards for these 2 things, the way they generate rewards for these 2 dimensions is they'll take a bunch of responses, have human annotators score or rank how helpful or how harmless the responses were, and then that human annotated data is used to train a reward model, which can be used in a similar kind of reinforcement learning loop. That's all the technical details behind R1.0 and R1. One of the key contributions here is that since these models are open weight, they are freely freely hosted in a lot of different places. So you can go to DeepSeek's website directly. Together AI has DeepSeek V3, DeepSeek R1, and many distillations. Hyperbolic is actually the only place that I found DeepSeek R1 0 hosted, but if you know of another place hosting it, let me know in the comments. But also you can get this model if you have enough compute power. You can install these locally or on your own hardware, so you can use Ollama for that, or you can use Hugging Face. And Hugging Face is basically all these models and many other versions of DeepSeek and its distillations and fine-tunes that other people have created. I've actually linked these in the blog post associated with this video, so you can access the blog completely for free in the description below. What does this all mean? I know there's a lot of hype and news around R1 and what this means for AI and for OpenAI and stuff. I don't read the news, so I don't really know what all the buzz and commotion is all about. But from like a research perspective, the key takeaway is that O1 and R1 have shown us that reinforcement learning is a promising research direction. So the question here is, why should we care about reinforcement learning? And the key thing is that through reinforcement learning, LLMs may no longer be bound by existing human knowledge. So this was demonstrated about a decade ago at this point, I feel, by AlphaGo, which was a model trained to play the game of Go, and it was trained using reinforcement learning, and it actually beat the world's best Go player, or at least one of the best Go players in the world. And so the key thing with this plot here is that we can see that the version of their model that was trained only on supervised learning would get better and better, and got better pretty quickly, but then it never could quite reach the skill level of the top grandmasters in the world, because this model was just trained on grandmaster data. So if it's just trying to mimic the grandmasters, it's never going to surpass the grandmasters. But reinforcement learning is a different story, because in reinforcement learning, the model doesn't learn from examples of humans playing. The model learns on its own through trial and error, and its reward is whether it won the game or didn't win the game. And so through this process, the model is actually able to surpass human performance and actually teach humans some new ways and new approaches for playing the game of Go. And so transferring this idea to the domain of large language models, like, what does that mean? Are we going to have large language models that can reason better than humans, do research better than humans, that can do math better than humans, do science, do fundamental research? And so these are all open questions, and I feel like an exciting time for AI research, because it's really interesting to see where these reasoning models can take us and where reinforcement learning can take us with large language models. And so the description people have made about LLMs for a while is that they're just stochastic parrots. So they're just recalling and remixing and re-saying text that they read previously on the internet, which is fundamentally what they're doing when trained strictly on supervised learning. They're just kind of regurgitating and remixing information from its training data. But the promise of reinforcement learning is that these models can potentially transform from parrots into proper researchers and scientists and contribute new information, new findings, new insights, new ways of thinking to our collective knowledge, which would be very exciting indeed. And so that's it. I hope this video was helpful to you and gave you some idea of what is going on under the hood of these reasoning models. So if you enjoyed this and you want to learn more, check out the blog linked in the description, which is like a write-up version of this, as well as the different references. And with that, thank you so much for your time, and thanks for watching.